Okay. We are recording. I do want to... Sorry, we're late getting started. But... There we go. I did want to do a quick review of where we are, where we're heading. Sorry we missed class Tuesday. We couldn't afford that very easily, so I don't know. We'll have to be humping it to sort of get the... everything done by the end of the term, but I think we can probably handle this okay. Let's talk about where we are. We finished chapter 16 last time. That means the test for 16 will be the last 30 minutes today. Okay? You can have your formula and equation sheet. If you haven't gotten those together, you might want to do that for chapter 16. We didn't get to do the lab for 16, and actually you'll be doing most of the lab on your own, but I'll allow 2 hours for the lab as normal. It won't take us the full 2 hours, so the odds are today you're going to get out a little early, because the lab won't be a full 2 hours, and then you'll have your test. But I'll allow you the 2 hours in case it takes longer than I thought. So that means we start, and the first 2 hours will be in chapter 17. I don't think we'll come close to finishing the chapter. It's a fairly long and fairly involved chapter, so we'll get what we can done. Chapter 17 for the first 2 hours, the lab for the next 2 hours, and then the test for the last 30 minutes. Except the lab part and the test part, well, it probably won't take that long. Which is... We just lost 2.5 hours of class last time, so a full week's worth of class last time, and the first Tuesday of the term didn't have a full class then either because I was out with my wife's outpatient surgery, and then so we are sort of getting a little behind, but we'll try to catch up as we can. Now, another thing that I had hoped to do, but because we missed class, I couldn't project when we needed to do it. I need to call the planetarium at Sanford and see when we can schedule a trip. Here's sort of the bad news side of the coin. I'm going to be in Tuscaloosa all day tomorrow. We've got math meetings there, and we'll be leaving here shortly after 7:15, 7:30 in the morning. And we won't be back until 4:30ish or later in the afternoon. So I have 0 office hours tomorrow. Well, I normally have my biggest chunk, 4 office hours on Friday. Will not have them. So can't do anything then. Monday, I do have 2 hours office hours in the morning and 2 hours and 15 minutes in the afternoon. So that's my next biggest chunks of office hours. I'm going to try to get in touch with Mr. Weigel then and see if we can arrange a visit. If he says, yes, we can come Tuesday, will y'all be watching your announcement page or wherever you look, the emails and stuff like this, to be able to do it on Tuesday? Okay. I doubt if he'll say it that soon, but in case he said, hey, Tuesday's the only day we've got, then we'll have to do it for Tuesday. So I'll let you know as soon as I know, and like I said, that won't be any earlier than Monday. Yes.
What time will we be getting back from the observatory?
That's hard to say. It depends on when he wants us there. If he has something early, then we'll be going late, and we'll try to be back by 5:45. I always try to be here before the end of class normally would be. If he doesn't want to be late and wants us there early, then we'll be back in plenty of time, and we'll actually have some class left over at the end. So we'll go with that. I'm guessing the odds are he won't say, oh yeah, Tuesday's open, come then, But in case that's the only time he's got, that'll be the circumstance. I'll be asking mainly for Thursday, that way we'll have the whole class to talk about it. So I don't want to spend class time now making plans for something that may not happen then, so let's just see what happens with that. All right, any questions? Any questions on chapter 16? That's the Earth-Moon system. Okay, so let's get going where we left off last time. This is on page 439, crystal structures. Now, remember what it took to be a mineral. Naturally occurring, okay, that means it occurs in nature, not man-made. Inorganic, that means it doesn't come directly off of any living thing. Solid, okay, certainly. Made up of elements and compounds, certainly. But those elements and compounds are in a fixed, rigid, crystal surface structure. That's what we're going to talk about now, the crystal structures that minerals do show up in. Okay. Now remember the chapter says rocks and minerals, but we're doing it in the other order, minerals and then rocks. Because rocks are made up of minerals, so we need to know the minerals first. And here are the crystal structures. They can be made up of one element, for instance, diamond, carbon only, naturally occurring diamond, carbon only, and it's definitely a crystal structure. The hardest crystal structure naturally occurring that we know of in nature. Okay? Or it can be made up of more than one kind of elements. For instance, quartz, those sand pebbles that you get in your shoe or something on the beach, that's silicon and oxygen.
I thought quartz was like that purpley colored rock.
Okay? There are some quartz. Most pure quartz is whitish, clearish. If it has slight impurities in it, then it can get the purplish colors and things like this, reddish and others. I think we'll see a few samples of that, and some that I'll be showing you in this coming lab or the next lab. Maybe this coming lab after today's lab, and after we go to the planetarium if we do that first. But you'll see some different colors of quartz, not pure ones, but usually pure quartz is clear to whitish color. And we're going to get to this a little bit later too. Color is one of the worst things to try to classify crystals by, because a slight impurity can change the color completely. Now, how do we classify crystals? Well, we do it based on what they call the surface symmetries. Now, we say surface symmetries. To my mind, these are three-dimensional symmetries. Yeah, the surface symmetries are important, but they are built on three-dimensional structures. Now, don't feel like you need to know these names and be able to identify it. This is beyond the scope of this course, but this is just to show the various kinds of different crystals that you have out there and you can have out there, and how really beautifully nature is put together with these different structures. So we'll talk about, in fact, I'll show them now, that these are 6 of the major classifications, and then you can see there's a lot of variety within a given classification. So the first is called isometric. Now, any of you familiar with the root word there, metric? What does that mean? Anyone know? Measure. Okay? That's what it means, measure. The metric system is a system of measuring. Okay? Isometric. So this, how about the prefix iso? Anyone know what that means? Second? Okay, no, not quite. Let me give an example to see if this will help with it. Have you ever seen the weather maps? And they have those circles, and they're not circles, but different shapes on them. And they'll be around high pressure areas or low pressure areas. Those are called isobars, those lines that form those shapes around those centers. What those mean is equal barometric pressure. So if you have a high pressure system, then the bars around it will be progressively getting smaller, lower numbers of pressure. Low pressure, the bars around it, or the circles or shapes around it, would be progressively higher. So what's in the center is a low pressure area or a high pressure area. Are any of you at all familiar with a sport known as orienteering? Okay, that is a sport that is a lot more popular in Europe than it is here, but we do have clubs of it here. Someone goes out and sets up a course, generally out in the boonies, out in the woods. Okay, someone will set up. Yes.
I've done that in scouting before.
Yes. Okay, and they basically give you a map, a topographic map, and a compass, and that's it. And say, go find the stations, and the map has on it where those stations are. So that's all, and you have to find your way with the compass and go do it. Now,
It's usually very difficult.
yes, it can be quite difficult. Okay, we had an Italian kid live with us one year. It was his senior year of high school. He was born in the U.S. We knew his parents well. His father graduated with my wife in the doctoral program at UAB, and so we knew the family pretty well. And Giacomo was born after his dad and my wife graduated. His dad moved to Boston, worked for a pharmaceutical company for a few years, and Giacomo was born while they were living in Boston. Well, he was a U.S. citizen because he was born in the U.S. So he then the family moved back to Italy, and his two sisters were born there. Well, then later, when he was in maybe junior high and his sisters in elementary or early junior high, somewhere around there, they moved back for a year of postdoc at UAB, so we got to know the kids. Okay? Then they moved back to Italy again. Then my wife had meetings in Italy, and we went over, and by this time Giacomo was in high school. And he sort of entertained us when the parents were busy, the dad's still working, and the mom having to do a variety of things. So he entertained us some. And we got along just splendidly. I mean, just a fun kid. And it was a good visit. And we had a good time with the whole family. And based on that, his mom and dad had already, he's a really bright kid, had already been leaning toward letting him come to the U.S., wanting him to have the option of either doing university in Italy or doing it here in the U.S. And they thought he'd have a better shot getting accepted in the U.S. if he graduated from a U.S. high school. So they were looking for sort of exchange programs. And then about that time, we showed up, and we had a really good time with them. And they said, well, do you think? So they started looking at Birmingham, found a school that would accept him. And I would think about any school would have. But they asked us if we would host him. We said, absolutely. So he came over. Well, he had done orienteering in Italy, and he did orienteering here. He turned out making the U.S. national team. Of course, it's not a big sport here, but he made the U.S. national team, and they do competitions all over the world when he can. But he's also working on his PhD in physics, in Germany right now, so he's just all over the place. But anyway, on a topographic map, which you have in orienteering, what you have are called isoclines. Those are lines that represent, or curves that represent, same elevation. So iso means same measure. What do we mean here for crystals? Here's a cube. That is an isometric crystal. Notice here, each side of a cube has the same dimension. Each angle of a cube is a right angle, okay? That's an isometric crystal. But that's not the only one. Here's an octahedron. Octo meaning 8, okay? Hedron meaning basically sides. And these are 8-sided. There's 1, 2, 3, 4, 1, 2, 3, 4. And each one of the sides, those triangles are equilateral triangles. put together in such a way that you have equal sides again. But they're not right angles, but it's very much an equal-sided figure. Here's a tetrahedron. Okay, again, equilateral triangles, but 4 of them put together. 1, 2, 3, 4. Okay, 4 equilateral triangles put together. 4-sided, tetra meaning 4. 4-sided figure. Octahedron, 8-sided figure. This is a dodecahedron. Okay, that is 12-sided figure. I don't know if I can count them all off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, a 12-sided figure. And here's Corey. Okay. Each with equal dimensions. Now, certainly those angles are not equal, but all the sides have equal length. So, isometric meaning equal measure. And you can see there's a variety of crystals that would be classified as isometric crystals. Okay, another one is hexagonal. Hexo meaning 6. So these are 6-sided crystals. Your quartz crystal is basically a 6-sided crystal. And we'll see samples of this where you have now those little sand grains that get in your shoe or in bothering your foot. They are just very little pieces of that 6-sided figure. Actually, quartz is 6-sided like this, but with triangles on the top. So it's a hexagonal prismatic structure. This is a rhombohedron. That looks a lot like a cube, and it is a lot like a cube, only someone sat on it. Made an elephant sat on it. So the angles aren't equal, okay? But, and they're not necessarily equal sides, but it's a rhombus is a square, and this is a 3-dimensional square, which is a cube, but it's been tilted a little bit. That's a hexagonal. Why hexagonal? How many sides? 1, 2, 3, 4, 5, 6. 6-sided structure from the hedron. Okay, a tetragonal structure is 4-sided figure. This is 4 sides, but it's isometric. This is 4 sides, but not equal length. Okay, and it is topped and bottomed by crystals, 4-sided triangular on top and bottom, but rectangles on the side. Here's an orthorhombic, and I haven't quite figured out what that means. Rhombus, again, means a 4-sided figure, probably with not equal angle. How this is different from rhombohedron, I'm not absolutely sure, okay? But there is a difference between those two, okay? And that's a prism of that nature. Then we have a monoclinic, okay? And let's see what this is. Help me out. Cold, got it, okay? All right, anyone else come in since I called roll? Okay. Now, again, don't feel like you need to have these memorized or anything else. You don't even have to match them up. Just to let you get an idea of all the different crystal shapes that are possible. These are 6 of them, major systems. They can have variations on these and subdivisions within these. So the next is the monoclinic, and where that name came from, I have no idea, okay? And mono meaning 1, usually. Clinic, I don't know what that means. But that certainly looks like more than one of anything, okay? And that's a prism of that form. And then this is triclinic. And how this could be mono and that tri, this tri meaning 3, mono meaning 1, it is beyond me, and how this differs from either of these two. Well, these are the same. Well, I'm not sure. I don't know. There's are differences there. These figures and the text doesn't give enough description for you to tell that. But this is just an example of the different types of crystal structures you'll have. Now, when you do the lab for this chapter, which will probably be either next Tuesday or Thursday, depending on whether we go to the planetarium or not, what day we go to that. When you're doing the lab, there will be a thing in that lab It doesn't say crystal structure, I don't think. But you'll have ways of describing it. And they often use a series of numbers like 1103 or 121, things like this. And for a crystallographer, that defines which one of these you're talking about. So you'll see that in your lab, but again, we won't go into any detail on where those numbers come from. But that just describes the different crystal faces. Here are some examples of those. We saw, the last figure we did last time was the cubic structure of salt, sodium chloride. Okay? This is, and they have on in your text, the top of the salt shaker magnified big time, and you see the little crystals of salt there are little bitty cubes. So this is again, the structure unit for table salt, sodium chloride, is cubic. Okay? You can see these individual cubes. Again, this is magnified fairly greatly, but every one of these crystals is a little cube. Now, they're not perfect cubes because they have been crushed and banged around a lot, scratched and dented. Some of the corners worn off. And by the way, salt is easily soluble, so some of them could have actually dissolved away. Okay? But every one of these is a little cube. Okay? Now, on the other hand, this is quartz crystal. And like I said, this is a six-sided figure, 1, 2, 3, 4, 5, 6, with sort of the angles at the top. And they're not perfect crystals, but they're made up of crystals, okay? And it's sort of hard to see. Here's the top part, 1, 2, at least 4 or 6 sides there, and it's embedded in another rock. And we'll talk about this later. Crystals make up rocks, so you have crystals inside rocks, but the outer part of the rock may not be the same kind of crystal. So you'll have all sorts of things, and we'll see samples of that when we do the next lab. Okay? Just examples of crystal structures. Okay? Any questions? Again, nature has a beautiful array of variety of crystal structures to play with. Now, we're talking about minerals. We talked about what makes up a mineral, the various classifications. Now we're going to talk about the minerals we deal with in geology and science, physical science. And they basically fall into two big camps: the silicates and the non-silicates. Okay? Now this is talking mostly about the Earth's crust. We're not getting down into the deep parts of the Earth, just the Earth's crust. And remember, the lighter minerals made their way to the surface, the heavier ones went deeper into the substance of the Earth. Okay? So, on the surface of the Earth, the minerals are either silicates or non-silicates. Now, let me flash back, if I will, because I know it's been more than a week since we did this. So let's go back. Remember the Earth's crust? Oh, that was last chapter. Sorry, I forgot. Oh no, there it was. There it was. I went through it too soon. Okay, the Earth's crust. Almost half of it made up of oxygen. That's the ATE part of silicates, or carbonates, or sulfates, or whatever, all the things with ATEs, lots of oxygens in the solid mass of the Earth. Silicon, outside of oxygen, more than a quarter of the Earth's surface, the crust, is made up of silicon. So it's not at all surprising silicates make up a huge percentage of the Earth's crust. Now you get the whole Earth, and silicon drops to number 3, oxygen's still number 2, but iron takes over as number 1, because most of the interior of the Earth is iron. Okay? So that's just a flashback of that. 8 elements make up 98.6% of the crust. Only 1.4% not in those 8 elements. So, not surprising at all that silicates make up a huge portion of the Earth's crust, 92%. So the silicates are made mostly of silicon and oxygen, though they'll have other chemicals, elements, compounds associated with it. But your silicates make up 92% of the Earth's crust. That's why we can say silicates and non-silicates. Even though it sounds really special, silicates way heavy, non-silicates 8% of the Earth's crust. Now, these silicates are based on the silicon-oxygen tetrahedral unit. Okay, tetrahedron, remember back here, the tetrahedron right here. Basically what you have is a silicon in the middle with 4 oxygens at the corners. That's your silica tetrahedral unit. That's what they're talking about. Okay? Now, 4 major arrangements of those silicon-oxygen tetrahedral units. You can have the isolated tetrahedrons, just like that one that we saw there, and that would be represented here. And again, the silicon in the middle, and then oxygen at the 4 corners of that tetrahedral structure. Now, this is a good illustration. It's not proportional. The silicon part, is really pretty small. It's usually a +4 charge, which means it's missing bunches of electrons, and the nucleus is positive charged, the electron cloud is negatively charged, so if it's +4, it's sucked in all the electrons, so it's not very big spatially. Oxygen, however, is a -2. That means it has 2 extra electrons, so they get even wider than you would expect, because there's extra electrons and they're not as tightly held to the nucleus as the silicon would be, which has 4 extra, or a deficit of 4 electrons. So the oxygens are big. This is really a dumb way to picture it, but have you seen the Michelin tire dummy or whatever it is that it's made to look like a tire? He's all blown up around. Well, picture 4 big at the corner oxygens with 1 little silica in the middle you can hardly see. That's basically your silica tetrahedron, and that's your isolated tetrahedrons. A silicon in the middle with 4 oxygens around it. Now that overall has a -4 charge, because remember, the silicon is a +4, and the oxygens are -2 each, so it's -2, 4, 6, 8, +4, that'd be a -4 charge. So it's connected to something else. Sodium silicate, potassium silicate, calcium silicate, some other thing. This is the silica tetrahedron that is part of those structures. Okay, so you can have isolated tetrahedrons, or you can have chain silicates. That's what they're representing here. Now you see what I was talking about, the Michelin tire. The big circles here are your oxygens, and that little green circle in the middle, that's your silicon. Okay? Now these are more proportional. This would be better, and it's not a rigid triangular looking shape. It's a big rounded triangular looking shape. Okay. So here would be your chain silicates. What happens here, and this side of the tetrahedron here, is shared with the side of another. So now you have 1, 2, 3, 4, 5 silicons, but you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's no longer a 4-to-1 ratio, because 2 of the oxygens are shared by 2 different silicons. Okay? So you have this chain nature. It's not a straight chain, it's a wiggly chain. They call it serpentine-like, and that makes up your chain silicates. Now we have some of those who are our clays. Halloysite is one. There are a few others. Some of your asbestos or chain silicates, serpentine minerals. Okay. Then you have your sheet silicates. They not just form the chain here, but they actually form a two-dimensional sheet. So here, there's two pairs of oxygens that share on either side of a silicate. And this one actually has 3 or 4 silicates sharing in some of the options. So you have your sheet silicates here, and then you have what they call the framework silicates, which are bigger sheets but also three-dimensional. And I mentioned the clay minerals. Clay minerals are usually combinations of silicate layers, silica layers, and alumina layers. And you have 2-to-1 clays. These are sometimes your swelling clays. We don't have that many around here. Down in Selma, they have. Any of you from the Selma area have been down there? Okay. They say that in the summertime, in really hot, dry conditions, the soils will crack so badly you can stick your whole arm down some of the cracks. Those are hard to manage in agriculture. Good, rich, fantastic soils are hard to manage because they split apart and the roots get exposed. It's really hard to deal with. The roads they used to build over those, they would rock and roll because of shrinking and swelling. They just made a mess of a road system. So basically they have to dig out all those clays and put in a clay that doesn't shrink and swell. Most of the clays around here are kaolinitic clays. They are one-to-one structures. Silica, alumina, silica, alumina, silica, alumina. Whereas the 2-to-1 is silica, alumina, silica, silica, alumina, silica, silica, alumina, silica. Okay? With these sheets in between and alternating with alumina sheets, which are octahedral, not they're hexagonal, not tetrahedral. So, but they fit together really nicely. So those are your framework silicates. Still a silicate because they have a lot of silicate in it, but they also have alumina in it as well. And if you go back here to your structure here, you see aluminum shows up as number 3 here, okay, right after silicon in the surface crust. In the whole Earth, aluminum shows up as number 1, 2, 3, 4, 5, 6, 7, 8. Okay, I'm sorry, 7. 1, 2, 3, 4, 5, 6, 7. Okay, 7. Just before sodium and then the others. Okay, so it's much less common on the whole Earth, but number 3 in the crust. So alumina is largely involved there. Okay. Any questions on the silicates? Then we have the non-silicates. Now, it almost doesn't seem fair. That's all we had on the silicates, but we spend almost as much or more time on the non-silicate, but they make up only 8% of the Earth's crust. But they are an important 8%. To be a non-silicate, there are no silicon-oxygen tetrahedrons in the crystalline structure. Okay? So, and they make up the remaining 8% of the Earth's crust, and there are 8 groups of these non-silicates. Now, these are basically in order of abundance. The most abundant of the non-silicates, but nowhere close to what your silicates would be, are your carbonates. Okay? We in Alabama are pretty lucky. Most of our underlying bedrock is limestone. And limestone is mineral-rich carbonate. Most limestone is calcium carbonate, but some limestone is dolomitic carbonate, okay, which is a mixture of calcium carbonate and magnesium carbonate. And there's actually a town here in Alabama, fairly close by us here, I think. I've only been through it once or twice. I'm not sure I can get you there again, called Dolomite. You've heard of the town? Okay. That must have dolomitic limestone calcium and magnesium carbonate. Now, most of one of the uses for limestone, there are many, but one of them agriculturally is to decrease the acidification of soils. Soils that are too acid just are not very friendly to roots growing in. And to get good crops, you need to keep the acidity down, so you usually lime your soil with ground limestone, finely ground limestone. Most of the time, that's calcium carbonate. That's the cheapest, the finest grind, does the most effective job in liming the soil, reducing the acidity. However, it really isn't all that helpful to the plants. Plants almost always have plenty of calcium, and they really don't need the carbonate that much. However, dolomitic limestone with magnesium in it, magnesium and calcium carbonate, if this were springtime, and later this term it will be, you'll see little green leaves out there on the tree. You see the buds of them right now. What is it that makes the green leaf green? The grass leaves green. What is it that makes that greenness? Chlorophyll. Y'all heard of that, haven't you? Chlorophyll is an interesting compound. It's like a claw. It's a calcium structure, a carbon structure surrounding a central ion. And that structure of a claw-like structure with this carbon-based claw around the central ion is very similar, almost identical to what we have in our blood. In our blood, we have that same claw, carbon-based claw, with a central ion in it, only in our blood, that central ion is iron. And what is the iron used for? What is that? There is a name for that structure there, and you've probably heard of it. That's what we call hemoglobin. What does hemoglobin do for you? Anyone know? I know this is a biology class. Okay, it gets pumped by the blood, but what is it carrying with it? Second? Okay, it makes the blood red. You're absolutely right. And if the blood's not red, what color is it? Blue. Okay, your veins are blue, your arteries are red, generally. Okay? Now, this is physical science, not biological science. I understand that. The hemoglobin is what changes color. What the hemoglobin does, it hauls around the oxygen for us, okay, in the bloodstream. Because guess what? You need oxygen to metabolize your food. That lunch I just ate, my body is in the process, probably more likely the breakfast I ate this morning, is in the process of oxidizing that food. Hemoglobin is what does that. It hauls the oxygen in there, it burns the calories. Your sugars are carbohydrates, carbon, hydrogen, oxygen. And the oxygen in the presence of that actually is oxidizing or burning that, releasing the energy. That's why I can move my muscles. That's why I can see. That's why I can talk. That's why I can hear. That's why I can think. And all the time, this is oxidation. Oxidation is an exothermic process. That's why we have a temperature of about 98.6 degrees, right? Our surrounding temperature is no better than 70, 68, 70, maybe 72, I doubt it, but outside it's way colder than that, but we maintain a pretty good temperature, 98.6. Why? Because we're oxidizing. We're burning fuel all the time. And the hemoglobin carries the oxygen to the cells where they oxidize mostly sugars, some starches, some proteins sometimes. Hopefully some fat sometimes too, though I'm pretty slow about doing that, okay? But that's what oxidation is. Actually, you burn most of your fat at night because you don't have any carbohydrates intake, so you start breaking down the fats. Good thing to sleep well, you have more time to break down fats. Okay. Now, that's just one advantage of sleep. So, why did I get off onto that? That claw carries around the iron, which is vital to us to haul our oxygen. And when the iron is oxidized, it's red. That's the red blood cells, the arterial blood. But when the muscles and other things use the oxygen up, then the iron reduces its valence and becomes ferrous oxide, not ferric oxide. Ferric oxide is oxygen rich. Ferrous oxide is oxygen poor. That's blue. Okay? So that's what your hemoglobin does for you. Well, what does chlorophyll do for the plants? It's that same structure, that same claw, carbon claw, with an ion in it, but that ion is magnesium. And there's where your dolomitic limestone is so much better for your plants than calcitic limestone because it provides magnesium. And most of our southern soils tend to be low in magnesium. So it's a good idea if you are liming your soil to drop the acidity and increase production, use dolomitic limestone if you can. It won't drop it as fast, but it's a good idea to do. So those are two types of carbonates, okay? Dolomite, and by the way, that magnesium and chlorophyll, that's what takes the energy from the sun and converts it to build the sugars. So you see the hemoglobin takes the oxygen to break down sugars. The chlorophyll takes energy from the sun and builds the sugar from carbon dioxide that it gets from the air and water that it gets from its roots. Combines those together to give you simple sugars. Fructose, glucose, sucrose, those kinds of sugars. So those are your carbonates. The calcium carbonate, magnesium carbonate. You have some others. After that, we have the sulfates. Now, there's two major kinds of sulfates, too. You'll see these are pretty predominant minerals. Calcium sulfate, which we often call gypsum. And we don't have any sheetrock in this room, okay? But if you know what sheetrock is, the generic name, sheetrock is a brand name. The generic name is gypsum board. And that's, if you've ever messed with it, you see it's cardboard on either side, sandwiched in between that is a white, solid material. That's mostly gypsum. Calcium sulfate. Now, if any of you were peanut farmers, you would also know gypsum by a different name. They call it land plaster, which is they use for the peanuts. The reason for that, peanuts need a certain amount of calcium to peg. That's a strange sounding term. A peanut, what would you say another plant that would be closely kin to a peanut? If you're thinking things like pecans or almonds or walnuts, no, nowhere close. They are distantly related, but not close. The most closely related to the peanut is soybean, peas, field peas, powder peas, those kinds of things. Those are more like peanuts. It's just that peanuts, we call them nuts, they grow underground, but their blossom, and in fact, if you've ever seen a peanut plant when it's very, very small, it's hard to distinguish from a soybean plant. But what the peanut does, when it blossoms, the blossom comes from underground, comes up and pegs above the surface of the earth. That way the bees, the moths, whatever, can fertilize it. And then when it gets fertilized to make the seed, it goes back underground again. And that's why the peanuts grow under there. But they have to be fertilized above ground because they're just like a soybean or a pea or a butter bean or something like that. They have to have the blossom fertilized above ground, but then they peg back underground to develop their seed. And we call them nuts, but they're really legumes. They're really more like a pea or a bean, mostly like a soybean. Okay, now, why am I saying all that? In order for the peanut to peg and get fertilized and go back underground, it has to have a certain amount of calcium. And if it doesn't have enough calcium, then it doesn't work well. But the main source of calcium fertilizer, you would say, would be limestone. But limestone raises the pH, reduces acidity, and peanuts need a little bit of acidity. They need that to grow. That's why they're a good southern crop. They can't stand really neutral soil. So you don't want to treat the soil with limestone because that raises the pH. It reduces acidity. So what you use is calcium sulfate rather than calcium carbonate, calcium sulfate, because sulfate is a very acid. Think sulfuric acid. That's an incredibly strong acid. So calcium sulfate is neutral. It doesn't change the pH. Calcium carbonate would greatly change the pH. So that's why we use land plaster gypsum. Now, in these concrete blocks, there's a fair amount of gypsum in there, and in the mortar between the concrete blocks, there's a fair amount of gypsum in that too. It's mostly calcium carbonate, but there is some gypsum in there as well. If we had sheetrock walls, like the newer part of the building does, yeah, you would definitely have a lot of calcium sulfate. There's another sulfate, magnesium sulfate. This has a special name too, and maybe your grandmother used this some. Maybe you did too. It's called Epsom salts. Ever hear of it? I know my grandmother used to have the gout, and she would soak her foot in Epsom salts. Okay, and everybody claimed that is the best thing to work on it. But she also grew some of the most beautiful African violets of anyone I ever knew. And one of her secrets was, after she soaked her foot in the Epsom salts, she poured the Epsom salt water on her violets. A couple times she overdid it and killed them, but most of the time she got it just right, and they were gorgeous. Okay, but those are two types of sulfates: gypsum, calcium sulfate, and Epsom salts is magnesium sulfate. But there's plenty of other sulfates out there as well. Iron sulfate, there's plenty of others. The oxides. And guess what? Remember what I said the ATE was? Oxygens, and then the oxides are oxygen, okay? What an oxide is not combined with some other, like carbon or sulfur, it's just this anion itself. So you can have iron oxide, ferrous oxide, ferric oxide. You can have aluminum oxides. You can have just about any metal combined with oxygen makes an oxide. Carbon dioxide, okay? Actually, we drink hydrogen oxide. We actually call it by a different name. Hydrogen and oxygen. H2O. What do we call that? Water, okay? So yeah, there's lots of oxides. Now those aren't minerals, by the way, those are liquids. Okay. Then you have your sulfides. Finally something without oxygen in them. All of your silicates have, because it's ATE, they have oxygen in them. All your carbonates have oxygen, all your sulfates have oxygen. Of course, all the oxides have oxygen. Finally, the sulfides do not. That would be something like iron sulfide, FeS, okay? And that would be, that actually has a name, pyrite, and that has a more common name, fool's gold. It looks just like gold. I mean, you can almost spend it. It looks so pretty, but it's not. It's fool's gold. It looks like gold, but it's not. Okay? That's one type of sulfide. You have plenty of others. By the way, hydrogen sulfide. Have you ever smelled rotten eggs? What you're smelling is hydrogen sulfide. Okay? The sulfur in the egg yolk has oxidized and gives that awful smell. Okay? The halides, okay? Those also don't contain oxygen. What your halides are, meaning they're the halogens, okay? Your periodic table, which we won't deal that much with, but it is important, These right here are the alkali metals, the alkaline earth metals. And by the way, the alkali metals, lithium, sodium, potassium, you'll be hearing a lot from them. And your alkaline earth metals, really you don't hear too much about, magnesium, calcium, we've just been talking about both of those. Then you have your transition metals, they're in here. And then you have your non-metals over here with sort of semiconductor metals in between. But your very next to the last column, these are called your halides. Fluorine, chlorine, bromine, iodine, actinium is pretty rare, and we won't go any more of those. Then you have your noble gases, helium, neon, argon, krypton, xenon, radon, and on. Those don't combine with anything. They have perfectly filled outer shells. They don't combine with anything. These are very reactive. These are very reactive. These are somewhat reactive. These are fairly reactive. These can be all sorts of things. Okay? So those are your halogens are over in column 7. So these are the halides. See, these oxides and sulfides there in column 6. There's oxygen, there's sulfur. Oxides, sulfides, these are the halides. And that would be things like halite is sodium chloride, salt. Okay? That's the naturally occurring mineral that salt comes from. Okay? Now we get back to our high oxygen ones, the phosphates. Okay? There was one particular phosphate mineral called apatite. Now, that doesn't mean it's hungry. It's APA, not APE, apatite. And that's where we get most of our phosphate fertilizer. Now, if you've ever bought any fertilizers, you'll usually see 3 numbers on the back. Not all, but a lot of them will. First number, nitrogen, and the next 2 numbers are potassium and phosphorus. Now, all the plants need lots of nitrogen. Nitrogen is a building block for proteins. And we want proteins. We want to eat proteins, we want to consume proteins, so nitrogen is every protein. Potassium is pretty, that was over on column 1. That's a pretty, very essential nutrient. All plants need a certain amount of protein, of potassium. There's lots and lots of sodium out there, but plants don't use that much sodium. They need the potassium. There's a lot less potassium there. But we need potassium. We get lots of sodium, but we need, usually people need a little bit more potassium. Now my mom, yes?
I think potassium is like through vegetables, like greens.
What's that?
Don't you get potassium through like grains and stuff like your vegetables and fruits?
Yeah, exactly. Potassium is also a big source for it is bananas. Really great source of potassium there. But my mom, when she was getting fairly old, she got so her body just wasn't absorbing potassium too well. And so she realized that and started eating more bananas, stuff like that, but it still didn't keep up. And she would have swelling in her feet and ankles. A lot of old people do that. I can say this in the same sentence. But my wife's not old, but she's already having some swelling, in, especially her right or left ankle. Really, she has a lot of problems with it. Sometimes, other times it's not as bad. So anyway, a lot of people will have that. What they usually give for that is a diuretic, which pulls a lot of those salts out of your body, which causes swelling. But when they do that, they're pulling mostly sodium salts out, but they'll also pull out the potassium. When my mom had swelling, she was already having trouble with potassium, and she would take the diuretic to pull that liquid out, her potassium would drop really low. And a couple times, it's my sister, I was not living at home, but my sister swore she was about to die. Her color, she'd get faint, she'd get disoriented. Everything would just go haywire. They found out it was potassium. So she started taking big old monster horse pills of potassium, so many a day. and because she needed that potassium. And her body wasn't absorbing it well, so she took a lot. So that's number 2. Number 3 in the list is phosphate. Now, phosphate is needed by the plants in much, much smaller quantity than nitrogen and potassium. But yet, it's one of the big 3 numbers. The reason is, even though you give them phosphate, the soil captures the phosphate. The plants can't use the phosphate. It's really tough to get it because it's a really complicated compound. So phosphates are very important agriculturally. Well, we have just about used up all of the easy-to-mine phosphate in the U.S. What are we going to do when we use it all up? We feed the world. We used to feed China, but our trade talks have sort of, not our trade not talks have sort of ruined that, but we still feed a lot of the world. If our agriculture industry, and you don't think of us as an agricultural country, but we really are. We have some of the richest land. We have some of the best growing conditions. You know, we really do feed the world. And if we can't get enough phosphate, we could be in serious trouble. And the whole world could. We'd have millions of starving people if you can't get that. Now, the only reason we can do as well as we can, are doing now, is because of what they call the Green Revolution. There was a certain German chemist. His name was Franz, I believe it was, Haber. It's spelled Haber like it would be Haber, but it's pronounced Haber. And he came up with this process by which you could take methane gas, which is a natural gas, you might say, a very high carbon gas, and mix it with nitrogen from the air and a lot of heat and other things involved with it, and form ammonia. Once he did that, we had all the nitrogen fertilizer we could use. Before that, they relied on what they called sodium nitrate, which was the old farmers called sody, okay, and it was sodium nitrate was the name of it, which had nitrogen in it, and that's what they used to fertilize the plants. But you got very little nitrogen because you had all that sodium and all those oxygens. But with ammonia, it's in nitrogen, H3, which is not much. Hydrogen is the lightest compound out there, element out there, so you have mostly nitrogen, okay? So it's a very rich nitrogen source. Well, he came up with a way to manufacture that using the air and natural gas. It was an expensive process, but still quite doable. And he basically was the father of the Green Revolution because of that discovery. Now, you would think someone who had made that big a discovery, that fed that many millions of people, would be quite an honored chemist, wouldn't you? He's not. As I said, he was German. And as I didn't say, but sort of referred, this happened around he discovered this in maybe the 1920s or 30s or sometime like that. But what was happening in Germany in the late 1930s? Yes. And what was sort of an ancillary to that war? What were the Germans doing to certain groups of people? Specifically Jewish people, but also Roma people, and anyone they didn't care for. If they're not Aryan, they were suspect. They were sending them off to concentration camps and sending them into showers where they wouldn't be showered, but they would be poisoned. Well, Franz Haber was a very strong Nazi, and he was probably the head chemist for the Nazis, and he also developed many of the compounds that used to poison and kill and experiment on Jewish prisoners and other prisoners they had. They imprisoned a lot of communists too, and they were ruthless in their, well, guess what? No one with that kind of resume is going to be not a chemist. No matter how good a chemist he was, no one's going to give him a lot of honor. So Franz Haber is not one of those. But because of him, we got all the nitrogen fertilizer we could use. There's plenty of potassium out there. It's getting a little scarce. But the phosphates, oh man, we're using up most of the available apatite. And there's not another really good source for it. We don't know what we're going to do. Then the next of these non-silicates are hydroxides, which are like sodium hydroxide. These are really strong bases generally. And it will be a sodium and then an OH. That's a hydroxide. Okay, so there is full of oxygen too. And then you have your native elements, your gold, your copper, your silver, iron, those kinds of things. They come in number 8 out of your lowest 8% of the Earth's crust. Go down deeper, you get more of those heavy elements, but you don't get them on the surface. So those are the non-silicates. Okay? So here is a table that sort of outlines these. Now realize the table looks pretty balanced, but in reality it's not balanced. This is 92% of the minerals over here. This is 8% over here. They actually look like they're about even, if anything, a little heavier that way. Not in reality. Your silicates are 92% of the Earth's crust is silicate, only 8% non-silicates. So here's the breakdown. And in the silicates, we have three major classes. Ferromagnesium silicates. Anyone know what ferro means? Iron. Fe, that's iron. Fe2O3. I mentioned ferrous oxide, ferric oxide. These are your irons. Okay? So those that are high in iron are called the ferromagnesium silicates. Those that are low in iron or no iron are your non-ferromagnesium sulfates. Silicates, non-silicates, ferromagnesium, non-ferromagnesium. Pretty. You got it or you don't. Okay? But then there's a third class, and these are clay minerals. Clay minerals are really important, but they're really different too. They are silicates. Like I said, a tetrahedral layer of silicates, then eliminates, okay? Or 2 silicates and 1 eliminate, or whatever. But what they are other minerals that are broken down and then reformed crystals. Those are your clay minerals. What classifies a clay mineral is the fact that it's so incredibly tiny. Now, you might say, how tiny is it? Okay? I'm going to give you a gross description of how small a clay mineral is. Take a dime. A dime is about 1 millimeter thick, right? And if you took that dime and sliced the dime this way, not this way, this way, sliced it into 1,000 equal slices, I can't even imagine that. They would be 1 micron thick. And the largest clay mineral is no bigger than 2 microns. 2 of those 1,000 slices together, that's your largest clay mineral. So those are tiny. And I mentioned kaolinite. That's the one most prevalent here in the southeast. And I bet you every one of you has some kaolinite right now, somewhere close to where you are. Do any of you have a pencil? Okay? Yes, you just throw it down, okay? You know what the lead in that pencil is? How much lead is in that lead? 0. It's not lead. Yeah, you can call it lead, but it's made up of 2 things. Mostly kaolinite clay. But the ingredient that gives it the dark color is graphite, which is basically the soot that you would have in your chimney, or something like that. That's the dark part, but what makes it hard is the kaolinite. Okay? And The kaolinite is such small particle size, and it mixes with the graphite. Your harder number 2, 3, 4 pencils have more kaolinite, less graphite. Your softer leads, like number 1 and 2s, they have more graphite proportionally than the harder ones do. The harder ones have more kaolinite. Illite is a 2-to-1 clay. Kaolinite is 1-to-1. Silica, alumina, silica, alumina. Illite is a 2-to-1 clay. Silica, alumina, silica, silica, alumina, silica. There's others like montmorillonite and some of the others. And then your chlorites are almost a 2-to-2 clay. They come in bundles of 4 rather than pairs. They're not that common here in the Southeast. The illites, believe it or not, are pretty common in Illinois. Okay, I don't think the names are that connected, but that's where they are. So let's go back and look at some of the ferromagnesium clays. High iron content. Biotype is a dark iron, usually makes it dark. Dark but fairly hard and fairly common. Hornblende is a little darker even. Augite is quite heavy in iron. Olivine is, you have to get really deep into the Earth's surface to find that much olivine. All high in iron, very dark minerals. Non-ferromagnesium minerals, very little iron or no iron. Quartz is one example. Totally silicon and oxygen. No iron to do with it. So your lighter colored minerals, generally no iron. Muscovite is white mica. When it breaks down, it becomes the illite. So these two are sort of connected there. Your feldspars. Now those are alumina silicates. They all have silicates. But these are aluminum silicates, and these are broken down into 2 major classes and some of those into minor classes. The plagioclase of your feldspars are sodium and calcium feldspars. Your orthoclase is potassium feldspar. You don't need to know all this, but just that if you see these titles, think non-iron high silica. These are silicates that are low in iron. The ferromagnesium are silicates, but they're high in iron. The clay minerals are reconstituted minerals, very, very, very small particle size, but they're still crystals. Then the non-silicates that we mentioned before, carbonates or calcites, and I'll show you some samples of calcite in the first lab in this chapter. Dolomite and calcite is calcium carbonate. Dolomite is both calcium and magnesium carbonate. Sulfates, gypsum, and they mentioned anhydrite. And I've heard of that before, but I told you about Epsom salts. That's another one. The oxides, hematite is iron oxide, magnetite is iron oxide too. Exactly the same chemical structure. Anyone know a difference between hematite and magnetite? Same chemical structure, same appearance, same everything. It's got one difference between hematite and magnetite. What's the first 6 letters of magnetite? Magnet. This is iron that's magnetized. That's iron that's not magnetized. Otherwise, they're identically the same. Limonite, I can't remember what the, that may be aluminum, maybe? No, this is aluminum oxides. Limonite is some other oxide, I don't remember which one. The sulfides, I mentioned pyrite. Iron pyrite is fool's gold. You have sphalerite. I've heard what that is, galena, and chalcopyrite. This is, I believe, copper iron sulfide. The phosphates, the main one is apatite. That's A-P-A-T-I-T-E. That's your phosphate-rich mineral that we use. I worked for Southern Research Institute for 8 years, and I did a lot of projects down in Central Florida around Lakeland and Bartow area. That's where they do a lot of the phosphate mining. And when they do that deep mining from that, pull up and stuff, some of the waste material that they lay everywhere has a little bit higher than average uranium content. Not mineable, not marketable, but it does have uranium and therefore radium in it. And therefore you get radon gas out of it. And people build their homes on the reclaimed mine land, and then they get radon in the houses. Or they don't. It just depends on the luck of the draw there. And we were doing radon research down there, and I kept seeing all these Drummond trucks. Well, what they were is the sulfuric acid they get when they mine this coal and process some of that. They produce a lot of sulfuric acid from the coal because our coal is high in sulfur, and they extract that, send it down to Florida, and that's what they use to break the phosphate minerals up so they can use the phosphate. So Drummond was all over down there just like they're all over here. Halite is table salt. Fluoride is a magnesium or sodium fluoride is a fluoride. And then the native elements are gold, silver, copper, diamonds, sulfur, anything that exists just as an elemental mineral. Okay. Way more than you probably thought you ever wanted to know. Okay. All right. Here are some examples, silicates and non-silicates. Here's the dead giveaway. They're darker ones. Well, okay, taking it back. These are ferromagnesium silicates. These are generally non-ferromagnesium silicates. The ferromagnesium silicates, the darker the colors, are the augite, the hornblende, and then the biotite is the lighter, okay? A little less iron than the other two, okay? But they're all silicates. This one, the light colors of non-ferromagnesium silicate metals. The mica are these that are in flat sheets, okay? This one, and you see this one actually broke off of that. The mica, sometimes you can actually peel the sheets off of it. Very strong bonding two-dimensionally, but weak bonding three-dimensionally. Now they say that when the U.S. was going west, the wagon trains, the time when all that migration was going on, and they were building the Saudis, they didn't have much timber out in the Midwest, but they took big chunks of sod and built their houses with it. Well, when they went to do the windows, glass was very expensive. You had to ship it from back east, so it was very expensive, but it was also very breakable, so you could ship it out there and wind up having it broken, and then you paid for a lot of broken glass. They would actually, if they found any mica, they would tear those off very carefully into sheets and sort of piece them together and use those. They are translucent, not quite transparent, but they let enough light in that in their old Saudi houses, which were usually pretty dark, they let enough light in, and it was a lot cheaper than buying window glass. Okay? That's mica, a two-dimensional structure. White and pink orthoclase, that is your feldspars. This is top and, I can't read that, top and center, I think it says. Quartz, these are your quartz. Oh, look at that quartz crystal. Isn't that a beauty there? You can see that hexagonal shape with the pointed hexagonal top. This is another piece of quartz over here. That hexagonal structure is going this way. Compare that to the darkened ferromagnesium. Non-ferromagnesium, ferromagnesium. Now, here's something that you can remember if you choose to. Lighter color, also lighter density, because iron is much heavier than silicon. So iron is down around 26 in the periodic table, and silicon is way up in the low teens. I mean, very lightweight. So light colored, but also light density. Iron's heavy or darker color, but heavier density. Okay. Did we beat that horse to death? These pictures are in your text. You can look at them there. Okay. There's also in your text a picture that's not on the slide set here. Gypsum, which is calcium sulfate, hardness of 2, and we'll talk about hardness a little bit later, but it's a very soft material. You can scratch it with your fingernail, just like you can scratch gypsum board with your fingernail. But then the quartz, look at that beautiful quartz crystal you see in figure 1710. See several of those crystals. They're just absolutely gorgeous. Okay. So that's where we're moving into physical properties of minerals. So flip back a page to page 440, and now we'll see these. And basically this is going to be your lab for this chapter. Something based on these. One of the most obvious properties is, of course, the color. I think Thomas Earl already mentioned, I thought quartz was pinkish rock. It can be, okay? But color is not very useful in classifying. Lots of different minerals may be almost the same color, and the same mineral may have a variety of colors. If you even think about it, diamonds are usually crystal clear, but sometimes reddish, sometimes yellowish, sometimes brownish. You can have all different colors of diamond. Due to very slight impurities can change the color distinctly. So color is not very useful in classifying. Useful in looking at it. It can be influenced by trace impurities, trace minerals found in that. Now what's much better in classification is take that mineral, whatever color it is, and rub it across a board that's usually called corundum or some other very hard kind of thing like sandpaper. Think sandpaper, but it's usually harder than that. And do that, and it leaves what they call a streak. The streak is a color when it's finally powdered. That's a much more useful color distinction than the actual physical color looking at it. Much more consistent than color in classifying the minerals. But here is one that's really good. Hardness, and that's what I was talking about before. That is its resistance to scratching. And we have a scale called the Mohs hardness scale. It uses 10 test minerals with increasing hardness. And here that table is. The softest of these is talc. Its assigned hardness is 1. Now, maybe some of you guys may use it some, but I would think maybe the gals might be a little more. Have you ever used talcum powder? Can you think of anything softer than that? It feels so good to the skin because there's no grittiness in it at all. That's a hardness of 1. I mean, you could almost break talc with your fingers, certainly with your fingernails. Okay, softest of your minerals, the Mohs hardness scale, that would be number 1. Other things could be close to it, but we use talc as the reference, softest. Gypsum's number 2, and that's the figure you saw in your text, figure 1710A. A piece of gypsum and someone scratching it with a little piece of glass, okay, or plastic. Number 2. Gypsum board, you can do that with your fingernail. Okay? Calcite. Okay, that's the calcium carbonate. And you'll see some pictures of that, and it looks to feel pretty hard, but if you took anything like a nail or something, you could scratch it surface pretty easily. Fluorite is one of those halides that we were talking about. It's number 4. It's not very common. Apatite, one of the phosphates we were talking about, the phosphate mineral, that's number 5. That's around the middle. Orthoclase, which is one of your feldspars, that's number 6. The reference for number 6. Quartz. Now this is pretty hard stuff. That's what we make a lot of the sandpaper from. Quartz is pretty hard. But harder than that would be topaz. Topaz, I think, is classified say again? It's sort of a semi-precious stone. beautiful ring material and very, very hard. Okay. Corundum, remember I said that's what the streak was measured in. If you had corundum, well, and some sandpaper does have corundum in it. That's much more effective sandpaper than quartz sandpaper. And then the hardest in nature is diamond. Okay. All right. There are some common objects that sometimes are used, and I've already used a couple of them myself, for comparisons rather than these actual test minerals. Some of them are, your fingernail is about a 2.5. It'll scratch gypsum, but it won't scratch calcite. Okay? Copper penny, well, we'll say any penny. There aren't many copper pennies anymore. I think they quit making them several decades ago. The pennies you have today, they look like they're copper, but they're made mostly of some cheaper metal because copper is more expensive than a cent pound. Back when they started, coppers, they were about a penny each, while they used them. Now, copper is a lot more valuable than 1 cent for one of those, so they don't use pure copper anymore. But that would be about a 3.5. That would be between calcite and fluoride, especially since you don't have that much fluoride around. Okay? Ordinary glass is not quite like quartz, but it's similar to it, but less hard. That's between 5 and 6. Okay, and then a pocket knife blade, which is steel, is usually 5 to 6 as well. So if you had a piece of quartz, some of those beautiful crystal quartz, tried to scratch it with either a penny, your fingernail, ordinary glass, pocket knife blade, you're not going to scratch it because quartz is harder than that. It's the number 7. But with quartz, you can scratch just about anything except diamond. Okay, or corundum or topaz. That's why topaz makes it pretty nice. It's a beautiful color, but it also is very hard, so it's not easily damaged. But of course, the diamond is the most valuable because it's very hard. It's really hard to damage a diamond. Okay, you can't scratch the surface with anything. Okay, more of the physical properties. Besides color, streak, and hardness, then we have the crystal form. Okay, we've already talked about that. 6 basic groups were mentioned. They're related to the geometric arrangement of the atoms, and they're given these numbers, 121 or 113, or something like that, which is related to the cleavage, which is the tendency of the minerals to break along these smooth planes. That's related to the crystal structure. And so something can be cleaved very easily, or it can be very difficult to cleave. If it won't cleave, then it generally will fracture. Okay? So that's irregularity in broken surfaces rather than smooth broken surfaces. So cleavage and fracture usually go together. And in your lab, you'll find those two listed in the same table. Okay? Then there's luster. Now, luster sounds sort of like color, but it's not. It's sort of like streak, but it's not. It's kind of the surface sheen. Okay? Now, some of the types would be if something looks very metallic, like a metal, it'll have a metallic string, luster. Pearly means sort of a milky whitish. Vitreous means almost like water. Okay? Vitreous. There are others, I can't think of them right now, but you'll see those in the tables when you do the lab. Then this is the one that's usually the best, I think. Density. What density is, a mass to volume ratio. Kilograms per cubic meter. Now we'll also have weight density, pounds per cubic foot. Okay, or something like that. Now, especially if you use the SI units, kilograms per cubic meter, those are units. Those are measured. An alternative is specific gravity, which you take the density, the mineral density, and do the ratio to that of water. But water's density is 1 gram per cubic centimeter. Okay? So you're dividing by 1, but you lose your units. So if you have units, it's specific gravity. If you have no units, if you have units, it's density. If you don't have units, it's specific gravity. But in the SI system, they're the same numbers. Now, 2 different factors help make up the density of a material. First is, what kind of atom is there? And we've already talked about that some. If you're high iron content, iron is down here at atomic number of 26, atomic mass of 56. If you're high silica, that's atomic, where is it? I can't find it. There it is, okay. Atomic number of 14, atomic mass of 28. So you see the big difference in the atomic weight of silica, 28, and iron, 56. That's twice as heavy. So if you have more iron or these heavier materials in them, then you're going to have a larger density. Okay? But the other feature is how are those atoms put together. There are some close packing things you can just get more atoms in a smaller volume, so that will have a higher density. Okay? Here's sort of an unusual example, because you probably never heard of it, but here's osmium down here is 190, which is pretty heavy, right? But it's to the left of gold, mercury, and lead. Those are all bigger molecules than osmium. But osmium usually packs really tightly, so osmium density is quite often greater than that of gold, mercury, or lead. So it depends not just on the making up, the atoms making up the mineral, but also how those atoms are packed together in the crystal lattice, how close they are to each other. That also affects the density. Okay. We need to stop at 3:15 to do the lab, 5:15 or earlier to do your test. Okay, so don't let me run past that. There is a concept supplied. Oh, here he is. Good deal. Bertram. Okay. We're in chapter 17. We're just finishing up looking at physical properties of minerals around page 442 and 443. Okay. And they do give in the book, and not that we're going to do that much with it, but what we have is, let's focus on this concept of density since we're just talking about it. Density, the symbol for density, and I don't know why they do this, is rho. Now that looks like a P, but it's more like our letter R, but it looks more like a P. It's a Greek letter, but that's the one they use for density, which has neither R nor P in it or anything else. Okay, it's D, but you know the density is mass per unit volume. Usually little m stands for mass. Capital V stands for volume because little v stands for velocity. So use a capital V there. Okay, that's the Greek. Rho is the Greek symbol. Is a symbol that P-looking shape is a symbol for the Greek letter rho, and density is mass per unit volume. Now you also have weight density, which sometimes they'll do rho sub W, and that would be weight per unit volume. The reason they do that is in the U.S. customary system, pounds and things like this, we seldom, if ever measure mass. There is a unit for it. I think we talked about it before, a slug. No one ever uses that. So we use sometimes weight density when we're talking about U.S. measurements. Pounds per cubic inch, pounds per cubic foot. In the SI units, the mass is either kilogram per cubic meter, which is a huge amount, or a smaller amount, grams per cubic centimeter. And that's what our lab, we'll be dealing with grams per cubic centimeter. If we take that grams per cubic centimeter and divide it by the density of water, which is 1 gram per cubic centimeter, you get the same number, but without a unit. These would all be grams per cubic centimeter. Specific gravity does not have units. Because specific gravity, they call it SG, and that's the density of the mineral divided by the density of water. And since the density of water in the SI system is 1 gram per cubic centimeter, you're dividing by 1. So you lose the units, but don't change the number at all. Okay. Now they do have a couple of examples here. A 4.08 gram crystal, that's a mass, grams measures mass, of the mineral augite, that's one of the high iron content, measures 1.43 centimeters long by 0.98 centimeters wide by 0.89 centimeters high, and its cleavage causes it to break in a rectangular solid. What is its specific gravity? Okay? Well, the only reason they gave that rectangular solid is they mean you have a perfect little rectangle. So you can use these measures. So if you did that, multiply those three together, 1.43 centimeters by 0.98 centimeters by 0.89 centimeters, you're going to come up with a volume. And do they do it here? Yes. But they don't tell you what the number is. But they do multiply those together. It looks like that might be 1.25 cubic centimeters. Okay? So you take the mass, 4.08, divide it by 1.25, and you get a density of 3.26 grams per cubic centimeter. But as for specific gravity, divide that by water, which is 1 gram per cubic centimeter. You lose the unit, the number stays the same. 3.26, which is a very dense mineral because it has high iron content. It has a lot of heavier atoms making up the mineral. Then they say a 6.39 gram crystal of potassium feldspar, which you expect to be much lower density because it's a non-ferromagnesium silicate. It's 1.82 centimeters long by 1.18 centimeters wide, 1.16 centimeters high. It is a rectangular solid. Was its specific gravity? It's more like 2.56, which is typical of most of your soil particles and things like that. Their densities are around 2, 2.5, something like that. All right. So that's... wait, before you go, let me go on and give you your lab, so if you want to follow it on the YouTube. Oh, why is it upside down? Okay. All right. Yep, here it is. If you want to follow on YouTube, you should be able to figure out most of it.
Okay, yes, sir.
Okay. Some other people have been going and coming. I hope I haven't lost anybody. Sorry I leave for good, or just... No, she's still there. Okay. Okay, sort of anyway. Okay. We did have some more coming and going, and some going out. Okay. There was at the bottom of page 442 a Grow Your Own that's talking about minerals, by the way, so crystals, don't think it's talking about anything else. Okay, never mind. Okay. Now, from there, let's move on to, here's some more physical properties. These are just illustrations of this. This is that same, it's not the same picture we had, but this is gypsum, which even your fingernail can scratch gypsum. Its most hardness 2, your fingernail is 2.5. This is one of the beautiful quartz crystals, pretty good sized crystal, that will have a hardness of 7, that not much you're going to scratch that with unless you have a diamond. Diamond ring, yeah, you can leave a big gash in that. But will not anything that is less than 7 will not scratch that quartz crystal. Okay? And you see, look at that. Their color is almost identical. Just looking at them, you think they're very similar. Nowhere close. Gypsum, very soft. Quartz, extraordinarily hard. All right, now we move to the next section, and this is 17.3, mineral forming processes. How do these minerals form? Okay? Well, a lot of these, the formation is by two liquid environments. These are the most common. When I say liquid environments, that can be two different things. One is water solutions. Okay? Now, I don't know if this has ever happened to you. I've seen it happen. I don't know if it actually happened to me, but I've seen it happen before. You go to cook your butter beans, and you put your pot of water on, but you haven't put the beans in yet. You put it on the stove, turn it on, and you go on and add some salt to it, right? Because you know you're going to want to salt those beans a little bit. And the phone rings, and you go and get to talking on the phone. Forget about your pot of water boiling on the stove, and when you go in to get it off, the water's all evaporated, but what you have at the bottom of the pan? Salt crystals. So what happened there, you had salt dissolved in the water, but then when the water evaporated, aided by the boiling process, but when it evaporated, the salt didn't evaporate, and that built crystals. Now, if that had happened real slowly, as in you didn't even have the heat on, but it just evaporated due to dry air, those crystals could have formed to be quite large, okay? But if they form real quickly, the crystals tend to be smaller, okay? That happens in nature as well, okay? Yes, you can evaporate some of the water away, but you usually have plenty of water around. But what also happens is temperature. So let's say that, and I couldn't believe this, because I've always thought of the Gulf of Mexico as being a hot bathtub. It's, the water's almost, in the summertime, is tepid, warm, and you don't get much refreshment from going in the water down there. But I didn't realize that the Gulf of Mexico is so deep in some places until the Gulf oil spill a few years ago. That was a mile or more deep. And down there, no sunlight gets through and no warmth gets through. The temperature down there is awfully close to freezing. I never would have guessed that anywhere in the Gulf of Mexico, the water was anywhere close to freezing, because it's real close to the equator down, to the tropics down there. So I was shocked to hear the temperature of the water down awfully close to freezing. Well, the lower the temperature, the more your crystals are going to form. Because warmer water will just, the molecules move further apart, they can keep more things in solution. But as they cool, the things start falling out of solution. Okay? So the water solutions, the crystals form from highly concentrated ions. Either the water evaporates away, which is always happening in the ocean in the Gulf of Mexico. Water's evaporating, and the salts stay there, and then especially if they're way down deep, where it's very cold, they can crystallize out. And that's where most of your calcite comes from, your limestone comes from, your coal and other things could come from some of these water solutions. Your apatite comes from a water solution. A lot of those minerals are crystals formed from highly concentrated ions in a water solution. And the water leaves, for some reason or another, or cool so much that the minerals come out. The other liquid is on the other end. Definitely not cool at all. And this is magma. You go deep into the Earth's center, and you don't have solid rock. I mean, you dig down deep enough, you're going to hit solid rock. If you kept going down, because of all the pressure of gravity of all the things above it, it's just like rubbing your hands together, rubbing them together while you're moving them. They get really hot. Well, you do that with tons and tons and tons of overburden, and your rock actually melts and becomes magma. Molten or melted rock from which the minerals can crystallize. Now, this can happen way deep in the Earth's crust or below the Earth's surface, or it can happen on or above the Earth's surface. And when it does, depending on where it is, your crystal size will vary, and what's coming out of solution will vary. Now, if this magma, which is molten rock beneath the surface of the Earth, ever makes its way to the surface, then it becomes lava. Magma when it's below the surface, lava when it's on the surface. Okay? And lava rock will be usually pretty porous rock, low density. You've seen ads probably for lava. Okay. Now, what are the important factors here? I've already mentioned several of them. One is temperature. Temperature in your water solutions. Lower temperatures cause the minerals to come out of solution. Okay? In your magma, different minerals come out at different temperatures. We'll see that a little bit later. Pressure. Okay? Another thing, if you have a lot of pressure on, especially the magma, it can force things into crystals sooner than if you didn't have as much. That'll also influence the hardness, the density, and other things. So pressure is an important factor. Believe it or not, time is an important factor. The slower the process of crystallization, usually the larger the crystals are. The more rapid crystallization is going to be very small crystals, because they're all hardening really quickly. The slower the time, usually the larger the crystals. And then the availability and concentration of the ions in solution. We said here in water solution that would be highly concentrated to start coming out, so the availability and concentration of ions in the solution. Again, let's talk mostly about water, but in a little ways about magma as well. Now, when you see this term here, glass, you probably think of that, don't you? That is a form of glass, but it's not the most common form in nature by any means. What a glass is a rapidly cooled solid coming from magma generally that because it cools so rapidly, it doesn't have time to form a good crystal structure. So therefore, it is left with a sheen, a glassy look to it, and that is it acts like a solid, but it's not really a solid because it doesn't have that crystal structure. Now, I say that, and you might say, no, that glass is solid. I can tell it's solid. Some of the oldest glass like that on the planet is in some of the great cathedrals in Europe. And some of it has been in those windows for multiple centuries, right? If you were to go to that oldest glass and measure the top of that and the bottom, you'd find that the bottom is thicker. Because that really isn't a crystal structure. Those molecules are actually flowing past each other, but happening so slowly you can't detect it. And it takes literally centuries for them to accumulate and move. So actually, glass is a rapidly cooled solid, but you might say a amorphous liquid, okay, because the molecules still move past each other. Remember, in a solid, they're fixed in the crystal lattice. This doesn't have a crystal lattice, so those molecules can very slowly move past each other. So what they call it sometimes is a supercooled liquid, that over time, the molecules actually move past each other. Whereas a solid, they're fixed in shape, and they don't move past each other. Now, are any of you into the Game of Thrones, that TV series or show or something? I've never seen it, but I've read some of the books. And one of the materials that they use for the swords, that they can kill some of the, whatever those creatures are, lights or whatever they are, is obsidian. Obsidian is a volcanic glass. Why they chose that, I don't know. But anyway, I thought if any of you had followed Game of Thrones, you would recognize that word. But if you haven't, it's no sweat. Okay. Now, especially when we're talking about the magma, the cooling of molten rock, the Bowen reaction series breaks that down for you pretty well. Okay? Now, remember that all these things we're talking about are silicates. They're either high iron silicates or low iron silicates. Ferromagnesium silicates or non-ferromagnesium silicates. So they have some from both sides. And these depend on the temperature at which these various minerals come out of solution. Okay? Now this is sort of what happens in the steel mills down here. Are any of you familiar with the steel mills? I'm not very, but I do know they heat up that iron ore and the other things they do, and then they start skimming off the dross, the mess they don't want in there, the impurities. And some things will come out of solution, they skim them off. And finally they get the steel coming out at a certain temperature, and then it's all very, very highly refined steel. The same thing nature does. Well, it doesn't skim off things, it just drops them off, okay? So some of these silicates come out at very high temperatures, way deep. Others of them come out at cooler temperatures, closer to the surface, and then cooler and cooler. So this is what the Bowen's reaction series is doing. So let's, okay, in general, the silicate crystallization sequence, both from the ferromagnesium and non-ferromagnesium side. The ferromagnetic silicates crystallize at higher temperatures. They come out of solution at very, very high temperatures. The others come out at lower temperatures. They're richer and richer in silicon and not as rich in iron. So you'll see that in this diagram. Okay. Now there's two legs here. I'm not going to say my gut feeling the temperature scale is not the same on both of these, but I don't know that for sure. Okay? But over here you have the ferromagnesium silicates, those high in iron. And way, way down deep, at really high temperatures, your olivines come out. Very high iron content, very dense materials. Then after that, the augites come out. Not quite as high in iron content, maybe not quite the density, but still really dark iron-rich rock. Then your hornblends come out at slightly lower temperatures, okay, as they cool a little bit more, your hornblends come out. And finally, your biotite. And notice here the way they colored it, biotite is the lightest color, probably the lightest density, least of iron, but still a ferromagnesium silicate. Still has plenty of iron in it. Okay. Now, over on the other side, these are your non-ferromagnesium silicates. And again, I bet you these temperature scales are different. They make them look like they're the same, but I bet you these are cooler than those. But I can't say that for sure. So here are your plagioclase feldspars. All these are feldspars here down to somewhere in here, right here. This is where the feldspars leave off. So you have your plagioclase feldspars, which are high in calcium, one of the heavier, not nearly as heavy as iron, but heavier than most. And those come out. Then your sodium feldspars, and finally your potassium feldspars. Okay? And then you have muscovite, which is, I used to know what muscovite was. It's similar to the illite minerals that we were talking about earlier. Okay? And then finally, the last one out is quartz. Just almost pure silicon. Okay, silicon dioxide. The other have potassiums and sodiums and other things in them. These are almost totally silicon dioxide. Silicon oxide. They come out at pretty high temperatures. I mean low temperatures. much lower than the ones above. And they're almost colorless, clear, crystal clear. The others will be different colors, darker, richer colors, as soon as it came out. Higher temperatures. Okay. Any questions on Bowen's reaction series? I think we've just run out of time. Okay. We got a couple of slides to go. The first of these is this one, minerals formed at normal temperatures. Let me see if I can find that one here. I don't see it here. Okay. Anyone see a slide number here? I don't. Okay. I'll try to hit that slide next time. Sometimes it'll point me right there, other times it forgets. And we're almost through with minerals, about ready to start on rocks. Okay? So we'll go from there. Let me go on and end this then. Okay. And let me pass out to you your labs for this week. Well, it is this week. I was going to say it should be today, but today is this week. Okay. Oh, me. Every time I turn these upside down. Rushed down lunch today. I only had less than half an hour, and I'm feeling awfully dehydrated. So first thing we're going to do probably is take a break, and oops, I went too far. Here we go. Yeah. Well, I'm not there yet. Here we go. All right. I think I'm at the right place now. All right. Today's lab, and I'll turn that back on in a minute, is Phases of the Moon. Again, this chapter, I call it the Earth-Moon System. So the chapter title is Earth in Space. So we talked almost as much about the moon as we did about the Earth, maybe not quite as close. But today's lab is talking about phases of the moon. Is there any other lab you're missing? I think you'll be able to hear on Peggy's screencast-o-matic, which you need to take one side, pass two back. Okay. Now remind me in about 30 minutes to call roll when it's officially lab time, but we're going to go and do the lab now. All right. There's a lot in the first page about the moon. They mention several ways that the moon is used. Moonstruck, fallen hopelessly in love or something like that. Lunatic, maybe along the same lines. I don't know. I'm sorry. Means sort of crazy. Somehow the moon is associated with that. Moonshine. Y'all would know what that was. But anyway. That's not how bright the moon is, I don't think. Okay. There's a few things that are completely wacko here. I see other languages are rooted in the base ME meaning measure, I guess. So maybe that's where that came from. Okay, you can read that to your heart's content. But what you're going to do, and this starts at the bottom of page 379, using about 6 observations of the moon over a 2-week period, you will examine how the moon does 2 things: changes position in the sky and how it appears as it does change its position. Now again, you're going to be looking about 6 different times. You're going to look at the moon over a 2-week period. Now if you think of that, 2 weeks is about 14 days. 6 times you're going to look at the moon. It's about every other day. If you can hit every other day, you'll get 7 observations. You're going to shoot for at least 6. Okay? That's what we're shooting for. So if you flip the page here, part A is going to be the observations you're going to be making of the moon. And you're going to do this over about a 2-week period. Now, I don't know if this is a good time to start that 2-week period or not. I would say not, because the moon just, what was it, last Sunday night, was it, that we had the lunar eclipse? That would be about the best time to see the moon, meaning you had about 1 week before that you could see it, and 1 week after that you could see it, and we're near the time that you're not going to see it again. The moon's going to be on the other side. So you probably won't start this right away, but you can get ready for it. Okay? A complete cycle of lunar phases requires 29.5 days. We won't see all those from a given time. You'll follow the moon for at least a half cycle, so your observation will spread over the course of about 2 weeks. During that time, you will be recording 2 ways, well, both the appearance of the moon, that is, how much of the lunar disk is illuminated, and also the position of the moon. But you'll do the position of the moon 2 different ways. How is the moon positioned relative to Earth landscape items, and how is it positioned relative to stars? Okay? So you'll have 2 different observations of position and 1 observation of shape or appearance. Okay? So that's what we're getting for. So choosing a location. This is what you can do now, and I would get into the practice of, looking at it, not frequently, but just seeing how things work for you. Okay? You'll need to choose a location. Now, what's important? I hope I'm still recording. I probably need to stand close enough for people who are listening at home. Okay. You'll need to find a spot with relatively unobstructed view of the horizon. Okay? Now, if you live in town, that may be hard to find. If you live out in the country, as long as you're in not a really wooded area, you might be a little better off. Okay? Or if you can easily get out to a spot like that. However, here are a few possibilities. Okay, now here's the second part. You'll need a large open space with a few low-profile landmarks near the horizon. That would be ideal. Okay? I'll come back and tell you a few possibilities. You will need a little ambient light to make some sketches. I'm not really big on the sketches. You might use them for your benefit. Okay? But you should not be near any bright sources of light. Now, that may exclude some areas. It is important that you use precisely the same location for all of your observations. So if you're make them from the middle of an open field or a parking lot or something like that, you need to somehow mark your spot so you can go back to that same location. It's the middle of an open field. Well, this is open, but I'm in the same place. You need to be as close as possible in the same place. So if you can, if it's open field, no one else is using, put your stake in the ground there, okay? a piece of hamburger. No, I'm just kidding. Okay. Or you can, if you can get some marking chalk like they use on baseball fields, or things like that, make your mark, or spray some orange paint, something like that, so you know you can go back to that spot. Okay. Now, they mentioned a couple parking lot. Those are usually open areas. That may not be bad. One disadvantage of a parking lot, a lot of them are lighted. That's also an advantage of a parking lot. You don't want to go into a dark parking lot, especially if you're in a rough part of town. So you might have some things to worry about there. I don't know. I know that when I drive home, I go past the old shopping center. I think it goes on both sides of the Vesper Superhighway here, and I don't think they have many lights on at night there, do they? So be safe about it. Maybe carry a big boyfriend or go in a group of people to make your observations or something like that. Be safe about it. But if you have one of those close by, a baseball field might be really nice as long as the lights aren't on. Okay? But if the lights aren't on, it may be a little scary, so have someone with you or something like that. But find something that's going to work for you. Okay? One term I had a guy, he sat right where you're sitting now in this class, really sharp guy, another really sharp guy, okay? And he was the work study person here on this campus, and he worked until 10 o'clock every night. So as soon as he got off work, he went out and made his observations, because he could go right out into the back parking lot. Now there were some lights on, so that was not as good, but there were not that many, and he made his observations from there. So if you can do it from a place like that, if you're near a school with a baseball field, a playground, or something like that, and you can get to the same place every day, that may work. Possibly the Birmingham campus, they have a field there. I don't know how well lit that field is at night. It looks like a practice football field, right? Is that really lit at night? I don't know. You're in town, and it may be too light. I don't know. You want as dark an area as you can without any bright lights, but you also need open area. Try to find a place. You can do that for the next couple weeks until the moon comes out again. But find you a place. And find you a place you can go to. Now, number B, timing your observation. You'll need to go to the same place every observation, but the other thing says your timing. It says your instructor will give you some general guidelines of dates and times. I just did. We're just about entering the phase where the moon's not going to be very visible, especially in the early evening. Now, if you're a super morning person, that maybe you get off work at 4 a.m. every morning and you come home, you grab a few hours sleep or something like that, you might want to do it right then. So the moon may be visible then when it's not at 10 o'clock at night. So you'll have to pick the time that suits your schedule better. But anyway, you can choose a time of night convenient to you for observing the moon. Once you choose a time of night for observing, it is critical that you make all your observations at the same time of night within 15 minutes. So that guy picked his time at 10 o'clock because he knew he got off at 10 o'clock. He could go right out into the parking lot and do his observations. Okay? They may have even cut down the lights by then. I don't know because the school was closed then. I don't know what we did, but anyway, that's, I think, what he did. Because the weather may hamper your observations over the course of the observing period, you do not want to let many clear nights go by. So you see, weather is not just whether it's raining or snowing or not, it's also how cloudy it is. A cloudy night, you're not going to be able to make these observations as easily. And certainly if it's raining, you can't make them. So you try to make your observations every other night, weather permitting. So let's say that you're probably not going to be able to do it tonight. Let's say you go out tonight. Tonight, I think it's going to be a really clear night. Last night, I think was, the night before were the really cold nights are the clear nights, by the way. Okay? And then you don't want to make it the next night. So then 2 nights from now, you go out and try again. Now, you won't be really doing this. But if that night is super cloudy or rainy or something, then do the very next night. Okay? You will want to get as close as you can to every other night, but if you have bad weather one night, then don't wait every other night. Go to the next night and then start your every other night again from there. Does that make sense? Okay. So you want to do it within 15 minutes every night, every observation you make within 15 minutes of when you did it before. And you want to go same spot. So those two things have to be the same. Same spot, same time. Okay. So here's what you record. In order to record the appearance and position of the moon, and they say about the scale drawing, if this helps you, do it. If it doesn't, just do it. But here's what I would imagine. Okay? Now this isn't a very good room to go by, but I'm just going to see if I can do it. Okay. If I were using, not this room, but this position, and you see there's a sign right over there. I can't read what it says because the trees are the way, with 2 poles, 1 open sign. That's going to be a good landmark for me. Okay? And let's see if there are any others. All right. There's a group of pine trees there that are thinner than the other group, and one sort of tall one right in the middle. That's going to be a landmark. Okay? Something like that. You look around your horizon, you need to have unobstructed view all the way around, and pick you a few landmarks. Not that many, just a few. Okay? Those are the things, if you're standing in the same spot, you'll be seeing those in the same position every night you do your observation, every other time that you go out. Okay? So, what you want to do is measure where the moon is from one of those landmarks. Okay? So let's say the moon seems to be over this one over here. Let's just say that corner is some type of landmark. Okay? And then I'm going to do, now here's what I suggest. I don't have one up here with me. Carry with you a clear ruler if you've got it. If you don't have a clear one, any ruler will do. A yardstick would do. Okay? Clear would be a little better, but any will do. And hold it so one end is on the horizon, and the other end is sticking way up there, and measure 0 at the bottom to up here, how many inches above the horizon it is from that landmark, or from that landmark, or from that one, just pick your landmark and do that. Where is the moon from there? Now here's another thing they don't mention here, but I think it would make a lot of sense if you had a compass with you. So when you're marking these, and they say make a scale drawing, here's my spot, and this one is south, due south, this one's due north, this one's northeast, northwest, something. Pick your, landmarks so you know where they are. And then when you're locating the moon relative to them, you can tell night after night which way the moon seems to be going. Is it moving from east to west, north to south? Where is it going? How is it changing night after night? Not, it's night after every other night type thing. Okay? So pick your landmarks. If you need to make a sketch, make a sketch. Whatever works for you. Okay? And they say you may want to initially go out about a half hour before your optimum time so you can make your sketch. Because the sketch can be done without the moon being there, and it doesn't matter what time. Those landmarks aren't going away. Okay? So do it a little ahead of time. Okay? Before you make your first observation. Now they have some guidelines here on page 381. If you don't carry a ruler with you, you can use this. The width of your outstretched hand is about 22 degrees. Okay? Now, when they say outstretched hand, that's 1 arm length away from your eyes. Okay? It's about 22 degrees. The width of your fist is about 8 degrees. The width of the 3 middle fingers, put all 3 out there one way, okay, is 5 degrees. The width of the index finger, about 2 degrees. Be sure you use it. Okay. Now, and you can use that. I think it'd be far better just use a yardstick and just do how many inches it is above the thing, and you can tell night after night where it's moving. Okay? You don't need to know degrees. Okay? Now, and then they say alternately you can carry a ruler with you to measure the dimensions of that. And they can use either centimeters or inches. I don't care. If you like centimeters better, that's the finer scale. Okay. To plot the position of the moon in the drawing, if you're making a drawing, you'll need to make two measurements. Okay? The first is your landmark, your physical landmark. Whatever those are, those. And then how high or whatever it is. If you have your compass with you, and we have some if you want to take one, but please bring them back. They're really cheap, but please bring them back. Or if you know your directions well, you can, like if you drive out there, if your car has things, point your car and due north, and then you look at your car and see whatever you want to do. Okay. But here's the two things you need to do. Where is the moon relative to the physical landmarks on the horizon? That's the first. How high, how far, which way it's moving, left to right, right to left, north to south, east to west, whatever it's doing. That's one. The second, though, is where is the moon relative to stars? So that first night you go out there, especially if it's a clear night, start looking for patterns of stars that you can pick out night after night. Especially if you're going at the same time, they're going to be in about the same place, night after night. If you go at different times, they're going to move some. So that's why you don't want to go at different times. So go out on some clear night before the moon's even out there and pick out some pattern of stars. It might be the Big Dipper. It might be Orion. It might be something that looks like a W up there. You just pick out some pattern that you say, oh, I can find that every night. I know where that is. Okay. So pick out the star pattern you can find every night. And then you measure, take your yardstick up there, how far is the moon and in which direction from that pattern of stars that I've been looking at. So you can tell where the moon is traveling night after night relative to the stars. So one measurement relative to the landmark, second relative to the stars. Okay? Now.
So like, for the thing for the stars, you would put like one end on, like the end with 0 on the constellation, and then put the other end on the moon.
Exactly.
All right.
And if you have a compass, which direction from those? If not, just sort of generally take a guess. And you're just recording this night after night, so the ultimate thing, and we'll get to that in a minute, is what question are you going to answer? We'll get there in just a minute. But here's the other thing that you do. Okay. Let's just go. I'll get to the third thing in just a minute. Here's the answer you're going to fill in at the end of your observations. You've made these observations, you've taken notes, you've recorded things, whatever you're going to do. Here's the question. How would you describe the night to night, it's really night to every other night, path of the moon with respect to the landmarks around your observing site? So if you've got those plotted, especially if you have a compass and you know what direction they are, it seems to be moving farther from the east to the west, north to south, right to left, when facing something like this. Give me an indication of where the moon is moving, observation after observation. That's the first. In which direction does the moon move respect to the background stars, night after night? Okay? One observation to the next. Is it moving further to the north, further to the west, farther, closer to them? What is it doing? Night, observation after observation. Okay? And then those are both at the bottom of page 381. If you turn to 382, there's a graph there. Okay? Now, the horizontal axis is the days of observation, and it shows 0 to 20. You're not going to use 20. Okay? You're going to use 0 to 15 at the most. Okay? But they have 20 there. Now, part of the reason for that, if you saw the moon for 5 days and it went away for 2 weeks and then came up for another bit of time, then you could use the first part and the second part. I think what will be best for you is to see it the first day it comes up and then follow it from then on. Then you'll have, and that'll be your day 0. Okay? The first day you see it, and it comes up, then go. Now that's at the time of night that you're looking. Okay? So that's going to be your day 0. Now, what it means by fraction illuminated. A full moon would be a 1 up here, okay? A half moon would be a half, wherever that would be. A quarter moon would be down here, 3/4 moon here. So you do, based on what portion of the moon you see, you estimate whether it's 0, which you probably won't see a 0 moon, a quarter, a half, 3/4, or a 1, or something in between, and this will be some sort of arc somehow across the thing like that. More than likely, in those 2 weeks, you'll see a full moon, okay? Whatever day that is, that will be, if that was day number 7 that you saw the full moon, that would be up here. Day before that, or 2 days before that, it probably wasn't quite full. 2 days after that, it wasn't quite full. So you'll see a pattern that way. So those are the 3 questions you make on your observations. Okay? Any questions about your observations? Set up, you've got from now till probably a couple of weeks to find your place, make some preliminary measurements, mark your spot, find the time that works best for you, pick out those stars that you want, pick out your landmarks. You've got plenty of time to do it. Sort of get into the habit of looking forward to going out at that time of night. Yes?
According to what I just looked up, it says that the moon should be visible tonight.
Should be visible tonight. Okay, look it up for 2 weeks. Yeah. Well, a week from tonight. Is it still visible? Now, he's looking that up. Let's move to the part we're going to do in lab today. That's the part you're going to do the next 2 weeks, or 2 weeks from whenever you can see the moon. You probably still can see it because it was visible a week ago. It's a full moon. You probably still can't see it. Now, it depends on what time you're putting in there too, doesn't it? What time did you put in?
From tonight.
Yeah, what time was tonight? Just sometime tonight?
Yeah, just sometime tonight.
Okay. Now, there's a little thing. If you can put in whatever time you'd like to see it, 10 o'clock, 9:30, 11 o'clock, whatever time you're likely to be out there looking every night. Like I put our dog out just about shortly after 10 every night. That's when I would do my observation from my backyard. Okay, that's when I usually do my observations.
All right, so by next week,
yeah,
we'll have a 4% visible.
4% visible.
And then it'll go up from there. So we should be able, well, we won't be able to see it on Saturday, Sunday, Monday, Tuesday, Wednesday, and then on Thursday it'll start to become more visible.
Okay. So that's just any time during the night?
That's anytime within the next week.
Right.
In the next 2 weeks, on the second week, on the 10th through the 28th, you should be able to see a lot of it.
Okay. That would be when I would target to begin on the 10th. Because you don't have 2 weeks from now, but you will have 2 weeks from the 10th. But go out and find your spot before then, and then once you start seeing the moon, start that night and go for about 2 weeks. Okay. Now, good. I'm glad you have that on your phone. But what I'm saying is, if you're choosing 10 o'clock at night, the moon may be visible sometime during the night, it may be 10 o'clock. But someone else is choosing 6 in the morning to be their observation, it may not be visible because it may have set in between 10 o'clock at night and 6. Or it may not, may not have visible. So I think what that's saying is visible sometime during the night. But you got to have a specific time. And you need to pick your time and see what's coming. Okay. So part B is lunar phase nomenclature. Okay? Now, we've already mentioned some of these things. When the moon is almost exactly between the Earth and the Sun, out of the Earth, the tail's going to be the Sun again. He's pretty bright. Okay? The moon between us, all we see is the dark side. And guess what? It's only visible in the day, but it's not the dark side, so it's really not very visible. So you're very seldom going to see a new moon. Okay? But that's called a new moon. And then the next night, it might be a little bit over here, and you'll get just a little bit at sunset, just a little bit of visible of that crescent moon for a little bit there, and then move on. Okay? So a few days earlier or later from the new moon, you'll have a slight crescent moon. Okay? Always the bright part of the crescent is going to be facing toward the sun. As the month wears on, the crescent gets bigger until when the moon's over here, the sun's here, the moon's here, I'll look at it at night, I see exactly half of it being lit by the sun. The other half is in the darkness. Okay? So that's a half moon. Between that, it was a crescent moon, just a little sliver, a bigger sliver, until half the moon's lit. And then when the moon's over here, bigger and bigger, until it's here, directly away from it. Now I see a full moon. Okay? Because the whole moon's getting lit, and I'm on the same side as that. And then it starts getting less and less, until here we're at half moon again. The half toward the sun is lit, the half back here is dark. And then it goes back to being a crescent, a big crescent, little, until it's just barely, then it goes back to the new moon. So that's our nomenclature. Okay? Now, I didn't quite give it completely. I gave crescent here, half moon here, and then I said it gets bigger and bigger until it gets to be a full moon. Well, this bigger and bigger phase, when it's more than half moon, going toward full moon, or going from full moon to half moon, that's called a gibbous phase. Gibbous, gibbous phase. Okay? So, new moon, crescent, half moon, gibbous, full moon, gibbous, half moon, crescent, new moon. Okay? Make sense? Those are the phases of the moon. All right. When it's growing night after night, little crescent, big crescent, half moon, small gibbous, bigger gibbous, full moon. When it's growing, you'll say the moon is waxing. In other words, getting bigger. When it's full moon, going gibbous, smaller gibbous, half moon, big crescent, little crescent, new moon, then it's waning, getting smaller every night. So that's the other terminology, whether it's waxing, getting bigger every night, waning, getting smaller every night. Crescent between the new moon and half moon, gibbous between half moon and full moon, gibbous between full moon and half moon, that'd be gibbous waning, half moon, crescent, waning down to a new moon. Okay. Those are the nomenclature. So if you turn to page 383, most of the rest of the lab is going to be on this page, a little bit on the not following page. And they have things in not exactly the backward order. We start in the middle of the page, we go to the bottom of the page, and then we go up to the top of the page. Sorry about that. Okay? So on the bottom of the page there, I'm going to try to draw this. It's going to take a little while. And this figure, if any of you have your text with you, and I think I mentioned this. Goodness gracious, I've got everything. Oh, I've got my text underneath. Say, where is my text here? There it is. Okay. This picture and what we're going to do with it is very like the figure in the text. And I told y'all we were going to do this on page 426 with two major exceptions. Okay, turn that on my projector. Okay. And I think you'll pick them out. Oh, there. I thought I'd lost my thing here. Okay. We're still recording. That's good. Okay. Two major differences. The projector's not on yet. Yuck. Watch it. I'm going to break something. Okay. I have to find my place again because that was holding my place. Here's the two major differences, but it's very similar. This one, the sunlight's coming from the left, shining on the left-hand side of the earth and the moon. Here, the sunlight's coming from the right, shining on the right-hand side of the earth and the moon. Second difference, this shows 4 moons, this shows 8 moons. Okay? So I will base mine on the one here, but it's going to look a lot like 426, only backwards and more of them. Okay? So, let's start by our sunlight is coming. Let me get my pen set up. Now, I'm tempted to use yellow, but you won't see it as well. So here's the sunlight coming in like this. Okay? Here's the Earth right here in the middle. Always the half of the Earth, so draw a vertical line through the Earth, right? Oh, it's already drawn there. And darken the half that's away from the sun. Okay? It's already done. The Earth is done right. The moons, you do just like that. They start with number 1 here. Mine aren't pretty circles. 2, 3, 4, 5, 6, 7, and 8. Draw a vertical line through each of those moons. As vertical as you can make it. And your moon should be a lot, well, yours are already drawn for you. You don't have to worry about it. Just draw your vertical lines and darken the back side of every one of them, the side away from the sunlight, just like I'm doing. Only you can do it a lot neater than me because you have prettier moons, right? You get the concept? Everybody see it? There's your first 8 points on the lab. That's pretty easy. Vertical line through every moon. The left half is darkened. The right half, leave white. Don't change a thing. Just like the Earth is. Draw a vertical line through it just like the Earth. The dark side, the side away from the sunlight, is dark. The side toward the sunlight is light. Those 8 moons, draw them in there. Okay? Okay, I've even numbered mine. Oh, no, I didn't. Sorry about that. Ooh, no. It helps to pay attention. Okay, sorry. Let's number them again. All right. I've got them numbered right? Yes. Really, wouldn't matter which way you do, but I'm trying to do it like the book. Okay. Everybody got your first 8 done, just like this. Okay. Now for your 8 at the bottom of the page, okay, what you're wanting to do is you're here on Earth, you're looking at moon number 1. What do you see? Nothing. You see the dark half of the moon. So number 1 at the bottom down there, and I didn't leave enough room, I didn't really plan ahead very well, did I? I'm going to do it here. 1, 2, 3, 4, 5, 6, 7, 8. Just barely got that in. This moon here, number 1, 2, 3, 4, 5, 6, 7, and 8. This moon down here, the whole thing is dark. Right? Is that what you see? Okay. Now, look up at number 2 moon here. This is about 3 days later. You look up and see number 2 moon. What do you see? You see just a little bit light, but all the rest of it dark. Okay? So number 2, draw your little portion like this and darken the major part. Always the part toward the sun is light, the part away from the sun is dark. You're beginning to see a little bit lit, but not that much. Okay? Look up at number 3. What do you see? Half moon, exactly. So this looks just like number 3. Do the vertical line with the back half dark. That should be pretty easy. Right? Any questions so far? Please ask. Don't let me leave you somewhere. Everybody got it so far? All right. Look at number 4. What do you see? I feel like a children's story. No, okay, never mind. What do you see? Number 4. Oh, you see most of the moon lit, but not all. So I'm going to make a little wedge back here and darken just the back part, and that's what will darken there. Okay? Most of it's lit, the part toward the sun, but the little bit toward the back is not lit. Y'all agree so far? Your picture can be a lot better than mine, okay? Look at number 5, and what do you see?
Full moon.
Everything is lit. So leave 5 just like it is. You see a fully lit moon, a full moon. Perfect. Look at, that was hard to draw, wasn't it? Okay. Look at number 6 and see what you see. Second? A little bit is dark. In other words, it looks just like 4. So just make you a sliver in the back and color that part in. Most is still lit, but the back part, little bit of the back part is darkened. Look at number 7. Oh, I'll let you get caught up. Sorry, I get going too fast. Okay, look at number 7, and what do you see? Okay, draw that vertical line. The back half, the left-hand side of the vertical line is darkened, and the right-hand side is lit. And look at number 8, and what do you see? Yeah, the more is dark, just a little sliver in front is still lighted. You see what I did there? Now my picture is pretty ugly. Yours is much nicer, I'm sure. I should have started off saying I highly recommend you use pencil, so if you do mess up, it's easy to erase. But if you got a pen and you're doing it carefully, that's going to be fine. Sort of late now, huh? Okay. Now we go up to the top of the page. Why it's in such a weird order, I don't know. I do know, but you see the figures are all put at the end, and they were referring to those before you got to number 3. So anyway, number 3. In the spaces below, write down the names of the phases corresponding to the sketches that you did down at the bottom, figure 49-2. Include whether the phase is waxing or waning. So what's number 1 called? New moon. That's all you have to put. New moon. Because there's nothing there, so it's not waxing or waning. It's right in between. It's a new moon. Okay? Number 2, what do you call that moon?
Vaccine.
What's that?
Vaccine. Vaccine.
One more time.
Vaccine.
Vaccine? Is that an Indian term? Oh, waxing. Okay. Okay, got it. It is waxing. But what do you call the phase of the moon?
Crescent.
Crescent moon. Crescent waxing. Got it. Okay, crescent waxing. Now, crescent is C-R-E-S-C-E-N-T. Crescent waxing. That's number 2. What's number 3?
Half.
Okay, it can be called a half moon, and what's it doing? Waxing also. Now, actually, for those who like football, you could call it a first quarter moon. No, I'm just kidding. That is another name for it. The first quarter from new moon toward full, that's called the first quarter. But I like half moon. That's what they usually call it. Half moon, but this is a waxing half moon because it's getting brighter every night. Okay? Number 4, what do you call that? A gibbous. What's it doing? Waxing. Gibbous waxing. Number 4 is a gibbous waxing because it's mostly lit, more than half lit. That's gibbous, and it's getting more every night, so that's waxing. Very good. Gibbous waxing. That's all you have to put.
What was number 3?
Second?
What was number 3?
Number 3, that was a half moon waxing. because it's getting more bright every night. It's half moon. Now you could have said, like I said, if you're a football fan, a first quarter moon. That's another name for it, waxing. But it's easier to write half moon waxing than first quarter. That's 3 words other than 2. So whatever you want to write. What do you call number 5? Full moon, and don't say waxing or waning because it's full. It's not getting any brighter or dimmer. It's full. That's all you have to put for number 5, full moon. Okay, what's number 6?
Gibbous waning.
A gibbous moon waning. Exactly. Sounds like that could be the name of a soap opera or something. No. Gibbous waning. Gibbous because most of it's lit. Waning because a little less every night is being lit. So it's waning. Number 7. Half moon waning this time. That's how you differentiate between 3 and 7. 3 is a half moon, but it's waxing. 7 is a half moon, but it's waning. 6 is a half moon, is a gibbous moon waning. 4 was a gibbous moon waxing. So between the combination of terms, every one is uniquely different. What's number 8? A what?
Crescent.
A crescent moon doing what? Waning, exactly. A crescent moon waning. Very good. Any questions on page 383? Not too bad, is it? All right. Now, this will require a little bit of thought. Oh, no, it makes my head hurt. Okay. I'm going to go in and shut this down. I'll leave it in case anyone needs it a little bit longer. Okay. Number on the back side, on page 384, at what time of day would you expect the full moon to rise? Full moon is going to be over here. Sun's over here. At what time of day would you expect that to rise? Notice?
Maybe about 4 o'clock.
Maybe a little bit later. Oh, wait, 3, 4 o'clock you talked about.
Like in the
Evening. I'll tell you a little bit later. Here's the key.
6.
The moon's here, the sun's here. So throughout that day, the moon is exactly opposite of the earth, of the sun from the earth, right? So when the sun is setting,
So 6
the moon is rising. So yeah, right around 6 p.m. Right around 6 p.m.
There's the answer.
That would be 5A. At what time of day do you expect the full moon to rise? Exactly opposite of the sun, around 6 p.m. Now, here's why I don't say sunrise. I would have said, sunset, because the sun is up for different hours of the day. Remember, this time of year, it's not up as long as it would be in July. So the sunset is at a different time. So around 6 p.m. should be a pretty good guess. It won't always be that, but pretty good guess. Number B. When do you expect a new moon or a very thin crescent moon to rise? Now, where is the moon when it's a new moon?
Black.
It's right between me and the sun, right? So when will it rise?
4, maybe.
Really? It's right between me and the sun.
maybe it's in
When the sun rises, the moon rises, right? Because it's directly between me and the sun. So what time approximately would the sun rise?
about 6 a.m.
About 6 a.m. Okay, about 6 a.m. Okay? And by the way, in the summertime, you will sometimes see that new moon better than you will other times because the sun is shining a lot longer, and you will actually see that moon, because otherwise it's going to be right at sunrise or sunset, and it's really hard to see. Okay.
There was one day at my summer camp
Yeah.
where the sky was so clear that we were able to see the moon around supper time.
Yeah.
Earlier than 6 o'clock and stuff.
Gotcha.
It was pretty cool.
All right. So a first quarter moon. The first quarter moon was the one that the half moon after it was a crescent moon before it's on its way there. So when would that first quarter moon to rise? When do you expect it to rise? So it's here, the sun's here. So when it rose,
June?
yeah, it would be right around noon. Okay? Yeah, right around the first quarter moon to rise. Okay? The third quarter moon to rise. Again, 90 degrees from the sun.
So not
Midnight. Very good. Right around midnight. Okay. The first quarter moon to set. Second, first quarter moon to set. Yeah, well, yeah, at midnight, exactly. Because it rose at noon, it will set at midnight. You're absolutely right. Very good. I can hardly hear you. And then finally, the new moon, or a very thin crescent moon, to set.
6
Which?
p.m.
PM, exactly, when the sun sets, because it's right there with the sun. Okay? So yeah, y'all got this good. Does it make sense?
Yeah.
All right. You know, I realized we didn't actually take a break, did we?
No,
I'm sorry.
let's take the
Okay.
test.
Do you need a break before we take the test?
No.
No? You want to go right for the
Yep,
test?
let's yes.
Now, does anyone need a break? If you do, let's take one. I mean, it's okay.
No.
Do you need a break?
No, I'm fine. But
Okay, then we're good.
okay, we're good then. We heard officially we're good. Okay. All right. Any questions on the lab? Take it home with you. Start your observations, setting up the timing, the place, the landmarks, set all that up, get all that ready until you start seeing the moon. So I would say every night, for a while, go out and check. Every night it's decent weather. Go out and check. The first night you see the moon, that's your 0 night, and then you start watching. If you've got everything set up by then, you should be okay. And you said start about the first of the month?
Around the 10th.
Around the 10th of the month.
10th
Start
of February.
set to February. Start looking now, okay? But it could be the moon's on the last few days now, so you don't want to do it now. But if you start the 10th of February and go through about the 24th of February, that will be perfect for this course. Okay? Now, let me also say this. Those observations, that's 3 questions. What you just did was a whole bunch of questions. Don't say, oh, I don't want to turn this in, I didn't make my observations. That's only 3 questions you're missing. So please hang on to this. Get the observations done to get those extra points, however many points that is. But please don't say, oh, I didn't make observations, so I'm not going to turn that one in. No, you got most of it done right now, those of you who are here. Those not here, hopefully you've been able to follow.
You haven't called roll yet.
Yeah, I do need to do that the second time, don't I? Knew there was something else. Zaria is still here. Marcus never has made it in, has he? We saw Marcus the first day of class and the first half of the next class and haven't seen him since. Rod is still here. Gavin, we haven't seen. Wait. Gavin, we saw the first part, but not the second part. He left before 3:45, didn't he? No, yeah, between. I think he did. I think he had to go to the Birmingham campus. Okay. Bertram made it in the first part, barely, but then has been here for the second part. Melanie hasn't been here today. She missed last time, too. Okay. Sonia is still here. I'm sorry. So, Samaya. Okay, sorry about that. My writing's so bad. Whoa. I just said you were still here and put an A there. Ew. Okay, Corey is still here. He made it in for the first part and here for the second. Thomas Earl is mostly here. Derek hasn't made it in since the very first day of class. I have never seen him. Okay, so I don't even know what he looks like. Seth is still here. Rashad, did we lose? No. Rashad, yeah, okay. Michaela is still here, eager to go. Okay, Cole is still here. Okay. Patel is still here, bright and sunny. Okay. Reggie, we haven't seen Reggie for a bit. Okay. Diego missed a day. And there I put a P. Okay. And Michael, we've only seen twice. Rhodesia is here. All right, good deal. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 4, 6, 8, 10, 12. Got it. Okay, so it's that gladsome time that we call test time. So let's see if I can find the test. Not deep enough. Still not quite deep enough. Ha! I think I hit it. Okay. Okay. I'm going to go and turn off the projector. Is that okay? Anyone need it any longer? I don't think we need to record any longer either, do we? So